Hello everyone, my name is Ruslana Fatkolna and we're from Group F. Today our group will be presenting about the project titled Design of Reactor Separation System for Methanol Production. But before we start our presentation, I will introduce to you our group members. So we have 5 members, which is Maya, Ruslana, Ian, Wong and Muhammad Afif Hazi. Through this presentation, we will discuss the process design, reaction selection, separation materials, simulation results, and the overall feasibility of our proposed methanol production system. Our presentation is divided into 4 main sections. First, we will introduce the project and our overall design basis. Next, we will discuss the reaction system, including the reactor pathway, catalysis, operating condition, and reactor design. After that, we will present the absorption-based separation process, followed by the regeneration strategy and our final decision. So let's begin with our background of the project. Methanol is an important chemical, is widely used to produce fuels, soils, acetic acid, and many other products. In our project, we designed a methanol production plant with a capacity 100,000 tons per year. Instead of using the traditional method that can depend on the fossil-based gas, we selected a more sustainable route, which is capture CO2 and hydrogen to produce methanol. The main benefit of this method is that CO2 can be reused as a raw material instead of being released into the atmosphere. However, the sustainability of this process depends on the using clear hydrogen and energy source. Therefore, our design considers the use of the low-carbon hydrogen and renewable energy. Our project has 2 integrated components. For reaction engineering, our objectives are to select and justify the sustainability or methanol production route, identify the main side reaction, determine appropriate kinetics and operating condition, and evaluate reactor performance in terms of the conversion, yield, and selectivity. For the separation process, our main objective is to purify the crude methanol using absorption. This includes identifying impurities, selecting sustainable adsorption, determining the absorption requirements, designing an absorption columns, and proposing an appropriate generator method.
So this diagram shows the overall process concept. Carbon dioxide and hydrogen are first fed into the reactor, where methanol and water are produced. The reactor outlet is then cooled and sent to a flash separator. This removes most of the remaining white gases from the liquid methanol stream. The crude liquid methanol then enters our absorption system. ADS-1, which mainly removes water, while ADS-2 acts as a polishing stage for remaining carbon dioxide. One important clarification is that our reaction engineering design was carried out independently using manual calculations and literature assumptions. The simulation was considered optional for reaction engineering and was mainly used to provide stream information for the downstream separation process design. With that overall process established, we can now look more closely at the reactor system. The selected production route is the direct hydrogenation of carbon dioxide. The main reaction is carbon dioxide plus 3 hydrogen molecules producing methanol and water. We selected this route mainly because it allows captured carbon dioxide to be used as a useful carbon feedstock. Another advantage is that although direct carbon dioxide hydrogenation is an emerging route, much of the existing industrial knowledge for copper-based methanol catalysts and fixed bed reactors can still be applied. Therefore, the route provides a reasonable balance between sustainability and technological feasibility. However, methanol formation is not the only reaction occurring in the system. Our desired reaction is carbon dioxide hydrogenation to methanol and water. The major competing reaction is the reverse water gas shift reaction, or RWGS, where carbon dioxide reacts with hydrogen to form carbon monoxide and water. This reaction is important because it affects methanol selectivity. In other words, even when carbon dioxide conversion is high, this does not automatically mean that all converted carbon dioxide becomes methanol. Some carbon dioxide can instead form carbon monoxide through RWGS. Therefore, when evaluating reactor performance, we need to consider both conversion and selectivity rather than conversion alone. For the catalyst, we selected copper, zinc oxide, and aluminum. This is a widely established catalyst system for methanol synthesis. Copper provides important active sites for the hydrogenation reaction. Zinc-containing structure contribute to catalytic activity, while aluminum provides structural and mechanical stability. For our literature kinetic basis, we preferred to Vanden Bush and Froment model. The important point from the kinetics is that the reaction rate depends on temperature, reactant partial pressure, adsorption effects, and how close the reaction is to equilibrium. As methanol and water accumulates, the net forward methanol production rate gradually decreases. So based on these kinetic and thermodynamic considerations, we selected the following reactor conditions.
Hi, my name is Ian and I'm going to be presenting Reaction Engineering Part 2. Alright, so for our selected operating temperature is 240 degrees Celsius with a pressure of 60 bar, a hydrogen to carbon dioxide ratio of 3 to 1, and an assumed single pass CO2 conversion of 30%. The temperature of 240 degrees was selected as a compromise. Increasing temperature generally improves reaction kinetics, but because methanol synthesis is isothermic, excessive temperature becomes thermodynamically unfavorable. High pressure is beneficial because the main reaction reduces the number of gas phase moles. Therefore, according to Le Chatelier principle, increasing pressure favors methanol formation. Our 30% conversion is used as a conceptual design assumption supported by comparable literature results, rather than being treated as a guaranteed industrial conversion. Okay, moving on to reactor material balance. The material balance begins with an annual target of 100,000 ton per year. Assuming 330 operating days per year, this corresponds to approximately 12,626 kg of methanol per hour or 394.08 kilomoles per hour. With our assumed 30% CO2 conversion, the required fresh CO2 feed is approximately 1,313.6 kilomoles per hour. Using the stoichiometry ratio of 3 moles of hydrogen for every mole of CO2, the hydrogen feed is approximately 3,940.8 kilomoles per hour. After reaction, the calculated outlet contains unreacted CO2 and hydrogen together with methanol and water. Most importantly, our inlet and outlet mass flow are equal, giving a 100% mass balance closure. For this preliminary balance, the RWGS reaction is acknowledged but not explicitly included. So the result represents as an idealized stoichiometric design basis. Okay, lastly, for reactor selection and sizing. For the reactor, we selected a multi-tubular packed bed reactor. This configuration is suitable because methanol synthesis is a gas-phase heterogeneous catalytic reaction and requires a large amount of solid catalyst. More importantly, the reaction is strongly exothermic. A multi-tubular configuration allows cooling medium to flow outside the tubes and remove the heat generated by the reaction. Based on our preliminary sizing, the required active catalyst bed volume is approximately 15.10 cubic meters. Using literature-based tube dimension, we estimated around 1,585 tubes and approximately 17.2 tons of catalyst. This value represents conceptual sizing and not a final mechanical equipment design. That is it for the reaction engineering design. I'll pass it to Afif.
Hi there, my name is Afif. So for adsorbent selection, we chose for ADS1, we selected molecular sieve 3A because it has a pore size of approximately 3 angstroms. So water molecules are small enough to enter these pores and become adsorbed. Methanol molecules are larger and are less likely to enter the pores, so methanol loss can be minimized. This makes molecular sieve 3A highly selective for removing water from the crude methanol stream. For ADS2, we selected Xylite 13X because it has a strong absorption selectivity, absorption affinity towards the CO2, the carbon dioxide. It is used after the dehydration stage as a polishing adsorbent to remove the remaining CO2. Therefore, the adsorbents were selected based on molecular size, adsorption selectivity, and their specific role in the purification process. Molecular sieve 3A removes water, while Xylite 13X removes residual carbon dioxide. All right then. So now it is for purification strategy. So to purify the crude methanol, we designed a two-stage absorption system. All right. So first, the crude methanol enters the ADS1, which contains molecular sieve 3A. The main purpose of this column is to remove water from the crude methanol stream. The dehydrated methanol then flows to ADS2. You can see it flows down there, and ADS2 contains zeolite 13X, which removes the remaining carbon dioxide and acts as the final polishing step. So the process sequence is therefore crude methanol followed by ADS1 and ADS2 and finally purified methanol. The stream properties and separation performance were obtained from our symmetry simulation. According to the simulation results, the final product achieved more than 99.5% of the purified, the methanol purity. And so, therefore, the combination of molecular sieve 3A and zeolite 13X provides an effective purification strategy for producing industrial grade methanol. Thank you. Right, before I finish my part, let's go look at the crude methanol and purified methanol composition. All right. So after the reactor and initial gas separation, the crude methanol stream is sent to the first absorption unit, that is ADS1. So for ADS1, the crude methanol mass flow rate is approximately 21,879. 0.58 kilograms per hour with a density of 881.178 kilograms per meter cube. Based on these values, the volumetric flow rate is calculated as 24.83 meter cubes per hour. The crude stream contains methanol, water, carbon dioxide, and hydrogen, and a small amount of hydrogen. That is, and the main impurity is water, with a concentration of approximately 291.17 kilograms per meter cube, which gives a water load of about 7,229.7 kilograms per hour. Right, so after water removal in ADS1, the stream enters ADS2 at a lower volumetric flow rate of 18.06 cubic meter cubes per hour. In ADS2, the remaining carbon dioxide concentration is approximately 109.3 kilograms per meter cube, corresponding to a carbon dioxide load of around 1,973.46 kilograms per hour. So these calculated component loads are then used to estimate the adsorbent requirements for both absorption columns. Thank you very much. I'll pass it to Warren.
This slide shows the operating conditions of our absorption columns. ADS1 used molecular flow 3A at 25 degrees C close and 6,000 kilopascals to remove water from the proud methyl. After that, the steam enters ADS2, which used the zeolite 36X at 25 degrees Celsius at 3,500 kilopascal to remove the remaining CO2. Both columns operate as fixed bed adsorption columns with downward flow, provide stable operation and high propagation efficiency. This slide presents the adsorption column design for ADS1 about 25,063 kilograms of molecular Sol3A are required. The adsorption bed volume is 32.99 kilometers with a column diameter of 1.71 meters and a bed height of 30.7 meters. For ADS2, around 7,376 kilograms of zeolite 30X are used with a bed volume of 10.93 cubic meters and a total column height of 7.61 meters. This dimension provides sufficient adsorption capacity while maintaining effective operation. This slide explains the radiation process. We selected the temperature swimming adsorption or TSA to radiate both adsorption columns, while one column is adsorpting impurities, the other is regulated using hot gas to remove the adsorpted water or carbon dioxide. After radiation, the bed is coated and pressurized before return to operation. This alternating process always continues menstrual propagation without interrupting production.
To conclude, this project developed an integrated reactor separator system for 100,000 tons year methanol production, a copper, zinc, or aluminium 2O3 catalysis, and multitubular packet bed reactor was selected for CO2 hydrogenation at 240 degrees Celsius and 60 bar. The reactor design achieved 15.10 meter cube catalysis bed volume with 1,585 tubes per 17.2 tons of catalysis. For purification, molecular size 3A was used for the water removal, followed by zeolite 13X for CO2 polishing. The system achieved 99.6 mole methanol purity, exceed the 99.5 industrial requirement. Overall, the process design demonstrates the integrated of the reaction and separation process for sustainable high purity methanol production. This is all from us. Thank you.